Welcome to all of you. Now we discuss about Unit 4 2022 Numerical Analysis Semester 6 2022 CC-14 Numerical Methods Unit 4. Question number 8. Show that an iterative method for computing the value of kth root of a is greater than 0 is given by xn plus 1 equal to 1 by k bracket k minus 1 xn plus axn by k minus 1, and also deduce that epsilon n plus 1 equal to minus k minus 1 by 2 into kth root of a. This is the epsilon n square, where epsilon n is the error at the nth iteration. What is the order of this iterative method? This question is a wrong question because this expression is wrong. So we correct this question. Actually, xn n plus 1 is the correct form is this 1 by k minus 1 xn plus a by x n to the power k minus 1. Let x equal to a to the power 1 by k. A is greater than 0, then x to the power k equal to a, and x to the power k minus a equal to 0. Let fx equal to x to the power k minus a, this equal to 0. Using Newton-Raphson's method, we have the iteration formula as xn plus 1 equal to xn minus fxn by f dash xn. Clearly f dash x equal to k into x to the power k minus 1. So we get, after simplification, this equal to k minus 1 bracket x to the power xn to the power k plus a the whole divided by k into xn to the power k minus 1. And this equal to 1 by k minus 1 bracket xn plus a by xn to the power k minus 1, n equal to 0, 1, 2, dot, dot, dot. Second part, reduce the error term epsilon n plus 1, nth iteration, for nth iteration. Assume xi is a simple root, real root of fx equal to 0, and epsilon k equal to xk minus xi is the error in the kth iteration. Then xk equal to xi plus epsilon k and xk plus 1 equal to xi plus epsilon k plus 1. From Newton-Raphson method, xk plus 1 equal to xk minus fxk by f dash xk. And so this xi plus epsilon k plus 1 equal to xi plus epsilon k equal minus f of xi plus epsilon k whole divided by f dash xi plus epsilon k. Now, f of xi plus epsilon k equal to f xi plus epsilon k f dash xi plus epsilon k square by 2 f double dash xi plus dot 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 dot, and f dash xi plus epsilon k equal to f dash xi plus epsilon k f double dash xi and plus dot dot by expanding Taylor's series expansion about the point xi. Since xi is a root of the equation fx equal to 0, so f xi equal to 0. So put here f xi equal to 0, and after simplification we get epsilon k plus 1 equal to epsilon k from 2 minus the value of f of xi plus epsilon k from this f xi equal to 0. So this epsilon k f dash xi plus epsilon k square by factorial 2 f double dash xi plus dot 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 whole divided by f dash xi plus epsilon k. So this is equal to f dash xi plus epsilon k f double dash xi plus dot dot, and dividing by f dash xi on numerator and denominator. So we get this, and this 1 plus f double dash j by f dash j epsilon k, and this whole to the power minus 1, and neglecting the epsilon k to the power cube and higher order of epsilon k. So we get this equal to half f double dash j by f dash j epsilon k square. Then epsilon k plus 1 equal to is k into k minus 1, j to the power k minus 2 divided by k into j k minus 1. Because fx equal to this, f dash x equal to this, f double dash x equal to this. So we find this. Hence epsilon k plus 1 equal to half k minus 1 divided by j epsilon k square. And since fj equal to 0, so j to the power k minus a equal to 0, hence j equal to e to the power 1 by k. J is a root of the equation fx equal to 0. So we put a to the power 1 by k in place of j, and this is the expression. Epsilon k plus 1 equal to half k minus 1 whole divided by e to the power 1 by k epsilon k square. Here the expression is this is the minus sign is here, so this is the wrong. Then epsilon k plus 1 equal to c epsilon k square, where c is equal to some constant half of k minus 1 by k root of a. And derivative method is said to be of order p or has a rate of convergence p if p is the largest positive real number for which there exists a finite constant c not equal to 0, such that mod of epsilon k plus 1 less than equal to c mod of epsilon k to the power p. The constant c is called asymptotic error constant. Hence from 4 we get this, the above method, Newton-Raphson method, has second order convergence because here this epsilon k square here. Next question, question 9. Explain whether one can use Newton-Raphson method to find a real root if fx equal to 0 has a multiple real root, how it can be generalized, and what will be its order of convergence. If alpha is a multiple root of a multiplicity m of the equation fx equal to 0, then we have f alpha equal to f dash alpha equal to f double dash alpha, if m minus 1th alpha equal to 0 and fm alpha not equal to 0. Now for a simple real root, Newton-Raphson method gives this xk plus 1 equal to xk minus fxk by f dash xk. And this xk, now fx equal to f of alpha plus xk, alpha is a root of the equation fx equal to 0, and epsilon k is the error at the kth iteration. And so expanding by Taylor switch, we get this. And since this alpha is a root of multiplicity m, so f alpha to f m minus 1th derivative of alpha vanishes. So we get f alpha, f dash alpha, f m minus 1th derivative alpha are all vanish. So we get only this epsilon k to the power m factorial m f mth derivative alpha, and this epsilon k to the power m plus 1 by m plus 1 factorial f m plus 1 derivative alpha, and so on. And similarly, we can find f dash xk equal to this, because this f dash alpha, f double dash alpha, f triple dash alpha, and f of m minus 1th derivative of alpha are all vanish. So we get epsilon k to the power m minus 1 by m minus 1 factorial fm alpha, and so on. Now from 2 we get epsilon k plus 1 plus alpha equal to epsilon k plus alpha minus f of epsilon k plus alpha divided by f dash epsilon k plus alpha. After simplification, taking the common term, this epsilon k to the power m by factorial m fm alpha, this is actually the mth derivative, this alpha, and this after cancellation we get this epsilon k by m and this denominator is 1 plus this term, so this 1 minus this term. After multiplying up to the neglecting the higher order, then epsilon to the power k and higher order, so we get, after simplification, we get this term. So epsilon k plus 1 equal to this, equation 5, and if m not equal to 1, m not equal to 1, m is the multiplicity of the root m, of the root alpha, then we get the epsilon k plus 1 equal to 1 by 1 minus 1 by m epsilon k plus order of alpha epsilon k to the power 2, which shows that the neutral reduction method has only linear rate of convergence for a real multiple root alpha for fx equal to 0. And note that for the quadratic rate of convergence of 5, we must have 1 minus 1 by m from the equation 5. We must have for the quadratic rate of convergence, if epsilon k square alpha, so we must, this term is 0 equal to 0, so 1 minus 1 by m equal to 0, so m equal to 1, and m is the multiplicity of the root, so this is absurd result because alpha is not a simple root, so m cannot be equal to 1. And second part of this question, this how it can be generalized and what will be its order of convergence. Consider neutral reduction method. Actually, this is the modified neutral reduction method for real multiple root in the form xk plus 1 equal to xk minus beta fxk by f dash xk, equation 6. Beta is an arbitrary parameter to be determined. If alpha be a real multiple root of multiplicity m, we get from 6 the error equation is this epsilon k plus 1 equal to 1 minus beta by m into epsilon k plus beta by m square bracket m plus 1 f m plus 1 derivative alpha by f m derivative alpha epsilon k square plus order of epsilon k cube. Actually, this expression comes from this calculation, this similar type calculation. So we get this error equation. This, if the method 6 is to have the quadratic rate of convergence, so this 1 minus beta by m equal to 0 must be true. So beta equal to m. Hence, the modified neutral reduction method for multiple root becomes xk plus 1 equal to xk minus m fxk by f dash xk, equation 7. And this is the general formula and the quadratic rate of convergence for determining the real multiple root of multiplicity m. Now we can derive alternative way this general formula. When the order of multiplicity m is known, consider fixed point relation x equal to phi x as phi x as x n plus 1 equal to phi x n, where phi x equal to x minus m fx by f dash x, x not equal to alpha. X is the nth approximation of the root alpha. Now we have fx equal to x minus alpha root to the power m gx and g alpha not equal to 0. Clearly, f dash alpha, f alpha, f dash alpha, f m minus 1 derivative alpha equal to 0 and f m derivative alpha are not equal to 0. Differentiating 2 with respect to x, we get equation 3, and from 1 using 2 and 3, we get phi x equal to this expression. Then phi dash x equal to, so this equal to 1 minus m into gx whole divided by m gx plus x minus alpha g dash x into minus x minus alpha into ddx of this expression. So phi dash alpha obviously equal to 0. Hence phi dash alpha equal to 0, equation 4. Again, xn tends to alpha as n tends to infinity. So xn plus 1 equal to phi xn gives alpha equal to phi alpha. Let epsilon n, that is equal to xn minus alpha, is the error in the nth approximation. Hence epsilon n plus 1 equal to xn plus 1 minus alpha, and after simplification we get this epsilon n plus 1 equal to minus epsilon n phi dash alpha minus epsilon n square by factorial 2 phi double dash alpha plus order of epsilon n cube. and this hence phi dash alpha equal to 0, so we get minus half epsilon square phi double dash alpha. Hence modulus of mod of this epsilon n plus 1 equal to half of phi dash alpha epsilon n square. And this shows that the order of convergence of this method is quadratic. Hence the introduction method is xn plus 1 equal to xn minus m into fxn by f dash xn n equal to 0, 1, 2, dot, dot for determining a real simple root of multiplicity n. Next question, question 10. Find the root of the equation x e to the power x equal to cos x using regular falsy method correct to 3 decimal places. Here fx equal to x e to the power x minus cos x. First we find f0, this is equal to minus 1, negative. F of 1, this is equal to 2.1779, is positive. So fx equal to 0 has a root lies between 0 and 1. Obviously this is a positive root. We take a0 equal to 0 and b0 equal to 1. The iteration formula for regular falsy method xn plus 1 equal to an plus hn, where hn equal to modulus of fan into bn minus an whole divided by modulus of fan plus mod of f of fbn. Now we construct a table, and this an negative, bn positive, fan, fbn, hn, xn plus 1 equal to an plus hn and fxn. Here first a0, 0, this because this negative, so we write here negative, and bn first b0 equal to 1, we write here f of 1 equal to positive, so we write here positive. So if an equal to minus 1 here, and if bn equal to b0 equal to 2.177979, and hn by this formula we can calculate hn, and so xn plus 1 equal to an plus hn, and find f of xn plus 1, and this is negative, so xn, this xn, actually this xn plus 1 put here this negative column, that is for an. New an is this, actually a1, and this is the b1 is unchanged, actually b01 is 1 also, and so on. Here the we want to find the root up to correct to 3 decimal places, so here we at least 4 or 5 decimal places check it. Here 5177 is 5177, so this 0.5177, actually this 8 correct to 3 is round off figure, 0.518 is the correct to 3 decimal, is the required root of this equation. Question 11a. Explain the method of fixed point iteration for approximating a simple real root alpha of an equation of the form x equal to phi x, where phi x and phi dash x are continuous on an interval about alpha. And question B, derive a sufficient correlation for convergence of the above method. Question C, find also the order of convergence of the above method if phi dash alpha not equal to 0. First, we find a simple real root alpha of an equation of x equal to 0. Then we express this fx equal to 0 as this x equal to phi x. The function phi x is known as iteration function. Clearly, alpha equal to phi alpha, because alpha is a root of the equation 1. So obviously, this x equal to phi x is another form of 1. So this alpha equal to phi alpha. So the point alpha remains fixed point under the mapping phi, and hence the root of 1 is a fixed point of phi. Here we assume phi x and phi dash x are continuous function on an interval about alpha. Using graphical or tabulation method, we find an initial approximation x equal to x0 of the neighborhood of root alpha. Then we find the n plus 1th approximation of alpha, and the iteration formula is given by xn plus 1 equal to phi xn is n equal to 0, 1, 2, dot, 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 so on. The convergence of this iteration method depends on the suitable choice of phi x and the x0 is suitable initial approximation of the root alpha. The sequence xn may or may not converge. If sequence xn converges, then it converges to alpha, and the number of iterations required depends upon the desired degree of accuracy of the root. Note that iterative method is self-correcting method. Next question, question B. The sufficient condition for phi x for convergence. This theorem, if phi x is a continuous function in some interval, closed interval AB, that contains the root and the mod of phi dash x is less than equal to c less than 1 in this interval, then for any choice of x0 belongs to the closed interval AB, the sequence xn determined from this iteration xn plus 1 equal to phi xn converges to the root alpha of the equation x equal to phi x. Proof of this theorem, the root alpha satisfies this, so alpha equal to phi alpha, and so alpha minus xn plus 1 equal to phi alpha minus phi xn. Using mean value theorem, we get alpha minus xn plus 1, this equals to alpha minus xn phi dash xi n, say. Xi n lies between xn and alpha, this xi n. So phi alpha minus phi xn equal to alpha minus xn phi dash xn. This is the mean value theorem from the mean value theorem. And this is the error term for nth approximation, n plus 1th approximation, this epsilon n plus 1, and this also epsilon n, and this phi dash xi n. So this n minus 1, phi dash xi n minus 1, and phi dash xi n. If we put this phi dash xi n, this, so this, of epsilon n plus 1 equal to epsilon 0 phi dash xi 0, phi dash xi 1, and so on, where x0 less than xi 0 less than alpha, x1 less than xi 1 less than alpha, and so on. If mod of phi dash xi I is less than equal to c for I equal to 0, 1 to n, then mod of epsilon n plus 1 is less than equal to mod of epsilon 0 c to the power n plus 1. If c is less than 1, so right hand side this tends to 0 as n tends to infinity. Thus, the iteration method converges if the modulus of phi dash x is less than 1. Question C, from question C, find also the order of the convergence of the above method if phi dash alpha not equal to 0. From equation 4, this is equation 4, alpha minus xn equal to alpha minus xn bracket phi dash xi n. From equation 4 we get this, so epsilon n plus 1 by epsilon n equal to phi dash xi n. Hence, taking limit n tends to infinity, this modulus of this limit n tends to infinity modulus of phi dash xi n, and this obviously less than equal to c less than 1. So fixed point iteration method is linearly converging, and this modulus of epsilon n plus 1 by epsilon n equal less than equal to 1, so obviously linearly convergent, that is the order of convergence is 1. And note that if limit n tends to infinity modulus of epsilon n plus 1 by epsilon n to the power p if equal to q, some positive quantity, then p, this is the power epsilon n to the power p, this power p greater than equal to 1 is called the order of the convergence of the method. Thank you for watching this video.